Today we are going to discuss about the normal and anomalous dispersion and related Cauchy and Sellmeier relations regarding these dispersion relations. So, from the optical properties of a material, we know it change or affect the characteristics of light passing through it by modifying its propagation vector or intensity. So, two of the most important optical properties are the refractive index N and the extinction coefficient K, which are generally called the optical constants. And the optical coefficients within this framework, we present the complex refractive index and the frequency or wavelength dependence of N, either the refractive index or the K, is normally called the dispersion relations. So how N and K are interrelated and how N and K can be determined by studying the transmission as a function of wavelength through a thin film or the material are mainly the focus of this chapter. So quickly going into the details of the normal and the anomalous dispersion, we all know that, let me, so this is the basic behavior of the normal dispersion, where we all know that this is the typical phenomena when a white light, such as sunlight or light from the incandescent lamp, is passed through a prism. We observe a color separation, right? The separation of the wavelengths. So light being electromagnetic oscillations, the different colors have different wavelengths and different frequencies in vacuum. For all of them move with the same speed, that is the speed of light c. So our eyes sense different wavelengths of visible spectrum with different colors. The separation happens because the different wavelengths have different refractive index. So whenever light enters a dielectric medium, this separation happens and the phenomena is known as the dispersion. So in simple term, the variation of refractive index with the wavelength. In other words, the characteristics or the variation of the frequency with the wavelength in a medium is dispersion. So Cauchy first studied the dispersion and gave a formula which described the dispersion in the visible range quite well. So the following formula is known as the Cauchy's dispersion formula, where n lambda is equals to a plus b over lambda square plus c over lambda to the power 4, where a, b, c are constants which depend on the medium, and experimentally the constants can be determined by measuring the refractive index for three wavelengths. So in usual condition, the first two terms would suffice to give an accurate value of n. And most importantly, the derivative of the refractive index, that is dn over d lambda, is nothing but the first is constant, therefore it becomes minus b upon lambda cube. Uh, given since A and B are both positive, so the refractive index decreases due to this negative sign with the wavelength in case of normal dispersion, right? So these are the basic characteristics of the normal dispersion. So if we going into deep details, uh, depending upon this dependence of the refractive index with wavelength, the most popular dispersion relation in optical materials is probably the Cellmeyer relationship, since one can sum any number of resonance type terms to get as wide a range of wavelength dependence as possible. So However, its main drawback is that it does not accurately represent the refractive index when there is a contribution arising from free carriers in narrow bandgap or doped semiconductors. So, uh, in case of Cauchy dispersion relations, what I mentioned above, uh, the visible spectrum region for various optical glasses and is applied to normal dispersion when n decreases. Sorry, this n decreases with increasing lambda. So the third term is sometimes dropped for a simpler representation of n versus lambda behavior. The original expression was a series like this in terms of the wavelength lambda or frequency omega or the photon energy h cut omega, as n equals to a0 time plus a2 lambda to the power minus 2 plus a4 lambda to the power minus 4 plus a6 into lambda to the power minus 6 plus dot 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 lambda until or unless it is greater than the threshold wavelength. Or in other way, it can be written as n equals to n0 plus n2 h cut omega whole square plus n4 h cut omega to the power 4 plus so on and so forth until or unless it is less than h cut omega th, as lambda and omega is the reciprocal of each other. Therefore, it is greater than the threshold of the wavelength and this is less than the threshold of the frequency. So where h cut omega is the photon frequency and h cut omega threshold is hc by lambda th is the optical excitation threshold that is in bandgap energy, where a0 a2 and n1 n2 n0 n2 are the constants. So it has been found in the Cauchy relation following this is like this formula, and this can be satisfactorily over a wide range of photon energies. So the dispersion parameters listed in the next slide for a few selected materials over specific photon energy relations. So Cauchy's dispersion relations given in the above selected equations were originally called the elastic ether theory of the refractive index. So it has been widely used for many materials, although in recent years many researchers have preferred to use the Cellmeyer relation, which I am going to discuss now. Now, this is the simple problem for the students as an assignments regarding the normal dispersion. I am requesting the students to submit the problem after the class. Going to the anomalous dispersion. So, uh, in the normal, we have the dependence that n has the disproportional relationship with the wavelength. In case of anomalous dispersion for material transparent to visible region, Cauchy's formula works very well, but in one further increase the wavelength, say, to the infrared. So one finds the refractive index suddenly decreases very fast and does not obey the Cauchy's law. So one now approaches to the absorption region, further increasing the wavelength. Once again, the refractive index becomes large. Again, the behavior is quite similar to the visible region for the increase in wavelength. If the range is increased further one, again observes another absorption band as shown in the figure. This is one band and this is another band. This is for the visible spectrum. This is the absorption bands, these dotted lines, right? So the pattern may repeat further as shown, giving many absorption bands. This dispersion is known as the anomalous dispersion. Uh, the first theory came from Sellmeier, who assumed that all elastically bound particles in the medium oscillate with a natural frequency omega naught, which corresponds to the wavelength lambda naught in the vacuum. So Sellmeier gave the formula like this. This is the extended term. So this reduces to the formula like refractive index square is equals to 1 plus E lambda square over lambda square minus lambda naught square, where A is a constant, and if one is away from lambda 0, it can be expanded in powers of lambda 0 by lambda, and one would get a formula of the Cauchy type. So, uh, and further details, the Cellmeyer equation is an empirical relation between the refractive index n of the substance and the wavelength lambda of light in the form of a series of single dipole oscillator terms, each of which is the usual lambda square over lambda square minus lambda I square dependence as discussed in this equation. N square equals to 1 plus a1 lambda square divided by lambda square minus lambda 1 square plus. So this equation is the special case where we terminated the higher order terms of lambda, and in this equation this lambda I is a constant in A1, A2, A3, and lambda 1, lambda 2, lambda 3 are called the Cellmeyer coefficients, which are determined by fitting this expression to the experimental data. So one can derive the Cauchy constant A, B, C in terms of the Cellmeyer constants A and lambda 0 square. So to explain many absorption bands, one has to assume different species of electrons with different natural frequencies omega j corresponding to the wavelengths lambda j in the substance, and then we can write n square equals to 1 plus sum over j times aj lambda square divided by lambda square minus lambda j square. So these are the typical values of the Cauchy constant as well as the Sellmeier coefficients A, B, C, and lambda 1, lambda 2, lambda 3 of some familiar materials like diamond, silicon, germanium, and these are the ranges of n minus 2, n0, n2, n4 in the energy units ev to the power minus 2 or ev to the power minus 4, and Sellmeier coefficients are termed as a1, a2, a3, a lambda 1, lambda 2, lambda 3 of silicon dioxide, and other BAF2 KDP type of materials. So a quick recapitulate of this previous, this one, sorry, Sellmeier constants, this A1, A2, A3, and lambda 1, lambda 2, lambda 3. So these are the typical values. So going to the quick details of the elementary theory, sorry, elementary theory of dispersion, which arguably said that the effect of dispersion when an electromagnetic field incident on dielectric. So we have seen that the displacement current is equals to the dielectric constant times the electric field, and this equation is can be written as D is equals to epsilon naught E, where epsilon naught is the dielectric constant of free space. So this is epsilon naught E plus P, and this is epsilon naught 1 plus chi. Chi is the susceptibility, electric susceptibility times E, where we have assumed that P is equals to epsilon naught chi E is called the polarization vector and is assumed to be linearly proportional to the electric field. So the factor chi is called the electric susceptibility of the substance, with the factor 1 plus chi is equals to epsilon R is nothing but the relative permittivity or the dielectric constant introduced in the previous class. So when an electric field is applied uh, to a substance, electrons of the molecules of the substance are displaced from their mean position as shown in the figure, and the electron does not leave the molecule as it is bound to it by some force. So in this situation, we say the substance is polarized. The polarization is measured by the quantity P and the net dipole moment per unit volume. And if one has n number of electrons per unit volume of the substance, the polarization is given by P is equals to minus NEx, where x is the displacement of the electron, this one, from its mean position. So where we are assuming implicitly that the field applied is along the positive x direction, the negative sign comes due to the negative charge of the electron, right? And hence displacement is along the negative x direction. So if the electron is little bit displaced from its mean position and left, it would oscillate with a natural frequency omega naught. So the positive ions do not move much due to their large masses. Now, if the substance is under time varying electric field E, the displacement will change with time. That is, it will undergo a forced oscillation. This kind of equations will be followed. X double dot plus Rx dot plus omega naught square x is equals to minus P by M E. This type of equations are derived in the acoustics while calculating the damping of the oscillator. So where the natural damping term is introduced proportional to the velocity. So we can recast the above equation by that. P double dot plus R P dot plus omega naught square P is equals to N E square M times E. Now we use the Maxwell's equation, curl of E is equals to minus B dot and curl of H is equals to D dot, to eliminate this polarization vector from the equation, and which eventually gives curl of B dot is equals to mu 0 D double dot. And if this is substituted in Maxwell's equation is being substituted, then curl of curl E is equals to minus mu naught epsilon naught E double dot minus mu naught P double dot. So grad square E is equals to mu naught epsilon naught E double dot plus mu naught P double dot. So going to the next equation, uh, mm, where the Maxwell's equation divergence of E is equals to 0 and have assumed permeability of the substance mu is equals to mu naught. That is B is equals to mu 0 H. So P double dot equals to 1 upon mu naught times grad square E minus 1 upon C square E double dot. So differentiating this equation with respect to time, we get del 2 del T2 plus R del T plus omega naught square P double dot is equals to N E square E double dot. So using this equation here, uh, now to eliminate P is turns out to be uh, this one, this one. This is the derivative part, del 2 del t square plus r del t plus omega naught square. And in terms of P, we have substituted this value here. So this times this is equals to mu naught Ne square over M E double dot. So now when a plane electromagnetic wave polarized along the x direction, then uh, Let me wait a second to write something. So when a plane electromagnetic wave polarized along the x direction, my E, my E or the x direction of E is nothing but the amplitude E naught times e to the power I k z minus omega t. And if as my wave polarized along the x direction, because Ey and Ez remains zero, so is incident on the substance with the frequency omega, have to substituting in the equation in the required value. This gives us this minus omega naught square minus I r omega plus omega naught square minus a square plus omega upon c square is equals to minus mu naught a d square omega square. So this is substituted here. So after some rearrangement of this equation, we get the value of k square as omega square upon c square 1 plus mu naught c square n square over m over omega naught square minus I omega minus omega square. Now omega by k, now omega by k is the phase velocity v, and the refractive index n is equals to c upon v, the speed of light at vacuum over this phase velocity. So we have the dependence of the refractive index on frequency as n square is equals to 1 plus mu naught c square n square over m omega naught square minus I omega minus omega square. So we find that in general the refractive index can be imaginary, okay, depending on the frequency, and this would lead to the absorption. Now if omega naught square minus omega square is far far greater than r omega, that is the damping is small and the absorption is neglected, so the refractive index is real in this approximation. So in vacuum, the wavelength is 2 pi c upon omega, and omega naught is equal to 2 pi c by omega naught. So we get the Cellmeyer equation, n square is equal to 1 plus mu naught c square n square by upon m omega naught, sorry, this is not omega, this is lambda, this is also lambda, lambda naught square minus lambda square minus lambda. This is turns out to be lambda square minus lambda naught square. So to get the a value as mu 0 n square lambda naught square over 4 pi square m. For the case of electrons of different restoring forces, we would write the polarization as P is equals to minus n Fj Xj for the electrons of different restoring forces. So the polarization is this, and if we substitute this polarization value, where Xj is the displacement of the jth atom, jth type of electron, and Fj is the fraction of that type and the total electrons available per unit volume in N. So proceeding as earlier, this would lead to the general Cellmeyer type equation, which is n square is equals to 1 plus mu naught n square over 4 n pi square m. This is pi summation over j fj lambda j square over lambda square minus lambda j square. So this is all about the derivations of the Sellmeier's uh, dispersion relation with a lambda and other values. So this is a very important concept in understanding the Cellmeyer relations in dispersion theory. So we are discussing about the dispersion and the scattering of the white light in terms of the different wavelengths of the visible radiation. The bend angle depends on the refractive index of the glass, and the refractive index depends on wavelength. So if glass weren't dispersive, we would not see the rainbow in the light refracted through a prism. So apart from this, we are recapitulating what we have discussed from the earlier slides of normal and anomalous dispersion. Okay, so what is the refractive index and dispersion? The permittivity is related to the screening of the applied field, that is E net is equals to epsilon naught over epsilon times E0, and the permittivity must be smaller at large omega than it is at omega equals to 0. But what it does in between can be complicated. I mean, let me discuss in the this slide that if your E net is equals to epsilon naught by epsilon times E naught, then in the relationship here, the curve goes like this. So this is the typical region of the in this axis. This is frequency, and this is refractive index -1. So in this region between where the uh, both this part, both this part and that part is normal, and in between this part is anomalous. So since epsilon over epsilon naught is equals to n square, similar statement can be made about the refractive index. So in case of normal dispersion, this dn d omega is greater than 0, and in case of anomalous dispersion, dn d omega is less than 0. So in between this part is where the derivative of the n over omega is less than 0, means the negative curve is for the anomalous one, and for the positive curve where this part and that part is the normal dispersion when the change of refractive index with frequency is greater than 0. So anomalous dispersion often occurs at frequencies where absorption is large. So this is also the behavior of the this curve shows. Since the resonance frequencies exist in many spectral ranges, the refractive index varies in a complicated manner, right? So this part is normal, this part is normal, again this part is normal, but in between the dotted lines, this was the abnormal one, sorry, anomalous ones. So these are the shaded regions where the anomalous dispersion occurs. So in the spectral range, if apart from wavelength, is if this is my okay, I am using the same slide here. If your y-axis, this is your x-axis, which shows okay, this is my x-axis shows omega and y-axis shows uh, refractive index. This is refractive index and this is omega. Then the usual curve becomes like this. Okay, so first anomalous dispersion occurs here. Second anomalous dispersion occurs here. The third dispersion occurs here. And so on and so forth. So this behavior is normal, here normal, here normal, here normal, and these are the parts where anomalous dispersion occurs. So in case of frequency, this part is the infrared region, this part is the visible region, this part is the ultraviolet region, and this part is the X-ray, right? So this illustrates a typical distribution of resonances with electronic resonances in the UV, vibrational and rotational resonances in the IR, and core electronic resonances occur in the X-ray region. So N increases with frequency except at anomalous dispersion regions, but the overall trend is a decrease in N as omega increases. So note that, sorry, as lambda increases, the index decreases. Thus, dn dn d lambda is less than 0. But again, dn d omega is equals to dn d lambda times d lambda d omega, right? And lambda equals to phi c by omega, which implies that d lambda d omega is less than 0. Therefore, finally, my dm d omega is greater than 0, right? So this is the normal dispersion.